The Wheatstone bridge strain gauge is a mainstay in the modern engineering world. It consists of two separate entities, a Wheatstone bridge, a device that can determine unknown resistances accurately, and a strain gauge, which varies its resistance when tension is applied along its active axis. This lab intends to test the correlation between the theories governing strain gauges and Wheatstone bridges in the real world. The Wheatstone bridge was not actually created by Charles Wheatstone. Instead, it was developed by Samuel Hunter Christie in 1833. His invention was intended for determining the unknown resistances of wires, but unfortunately, its creation went largely unnoticed by the scientific community. Enter Charles Wheatstone, a more renowned member in the Royal Society than Christie, who published Christie's findings again in 1843 in a paper titled The Becquerian Lecture, an account of several new instruments and processes for determining the constants of a voltaic circuit, giving Christie proper credit. His prestige brought Christie's invention to the attention of the Royal Society, and the bridge ended up taking Wheatstone's name in the end. To understand how a Wheatstone bridge strain gauge functions, we must first understand the basic principles that govern a strain gauge. A strain gauge is a sensor that uses its change in resistance to measure tiny deformations along a surface. This change in resistance is directly related to the strain in a beam, where the strain is the change in length of a member divided by its original length. A metal foil strain gauge works by deforming with the member that it is attached to. At the microscopic scale, this deformation changes the width and length of the foil inside the gauge. This change in length, multiplied by the resistivity of the gauge's metal, divided by the cross-sectional area of the wire, equals the resistance of the wire. As more tension is applied, more stress causes more deformation, which then causes higher resistance. Strain gauges can work both ways as well, with compression yielding lower resistance. Wheatstone bridges employ strain gauges in one of three configurations: quarter bridge, half bridge, and full bridge. A quarter bridge contains one strain gauge, a half, two, and a full bridge contains four strain gauges. For an ideal quarter bridge, R1, R2, and R3 are equivalent resistors. R4 is a strain gauge which has a resistance equivalent to the other resistors, R1 through R3, when no load is applied. Thus, when no load is applied, Vg is just zero. When the load changes, though, Vg will then change according to the new resistance. To calculate Vg, we take the change in the strain gauge resistance and divide it by its initial resistance. Finally, multiply that equation by the voltage of the source, and the result is a direct relationship between voltage and force that can be evaluated by a computer.
So you go ahead and get that set up, come down here. How are you going to acquire one sample on demand? You can have N samples, you can 10, 100,000, 20,000, or you can do continuous.
After we figured out how to turn on our voltmeter, the team began testing the resistances of the 4 ultra-low tolerance resistors and recording the values in Excel.
Okay.
The 4 resistors were measured and their values were interestingly much more precise than they were accurate, with the average rating for each resistor being 120.2025 ohms. In a scenario of a Wheatstone bridge strain gauge, the resistor precision is much more important than resistor accuracy, as each resistor should be as close as possible to the rest. So even with an average resistance of 202.5 milliohms above the rating, the maximum deviation from that average is only 32.5 milliohms, which is not only acceptable, but rather good for our experiments. It is worth noting that the resistance of the wires used was not considered before the measurement of resistance, which could explain the deviation for these ultra-precise resistors. After the resistances were documented, we turned our attention to the 2 potentiometers. After setting up our spreadsheet for both, we began wiring the potentiometer into our breadboard. Instead of hooking the alligator clips to the potentiometers, we used 2 jumper cables to give us a steady base to work with. Then we set the potentiometer to its lowest level and subsequently turn the dial one full rotation for each data point. At one point during our experiment, a turn was miscounted and our data was offset. This offset was discovered when one member noticed the values not coinciding linearly with the turns of the potentiometer. Data was retaken several steps back, which properly rectified the inconsistency. We then graphed our data to ensure our test resulted in a roughly linear trend for both increasing and decreasing resistances. The potentiometers were more difficult to measure. Both appeared to lag in resistance behind the actual turn of the dial. That means as the dial was turned to increase the resistance, the actual recorded resistance was slightly lower than expected, and as it was turned to a lower resistance, the reading was slightly higher. This is expected with most common potentiometers, and our data shows the low and high lag values of the potentiometers. Once those procedures were completed and we had grown more accustomed to the lab, we began working on the strain gauge setup. Due to unforeseen circumstances, the typical data acquisition hardware was not working properly, so we fell back onto a USB DAC. Differences between the two exist, but for our purposes, the USB DAC was acceptable. I got it. You're good. That was beautiful.
On the left scale, and they come down out to the lowest one, double click, and put a 0. And then up at the top, where you have to hit the up at the top, put 5,000. Okay. And then hit return. Yeah. Awesome.
Once Dr. Barnett suggested a better way to scale the y-axis of our graph, our data from the strain gauge came out very well. The Wheatstone bridge operated as intended, and as the beam was deflected from a subjected force, the strain gauge's resistance changed directly with the strain in the beam. We measured a 0.592-inch maximum deflection on the dial indicator provided. This coincided with 3,636 microstrain, which directly correlated with the voltage change of 1.9091 volts. As you can see in the graph of our recorded data, the strain varied linearly with the deflection of the beam. Separate trials of different deflection amounts, speeds, and consistencies all yielded similar direct correlation results. This indicates that our results verify the strain gauge's long-standing use as an effective way of measuring strain. Our main source of error, well, was ourselves. We're only humans, so a few issues hindered our progress. One such incident was an accidental short circuit that happened due to our wiring configuration. We didn't record any results from this mistake, but it did baffle us until we went back and reviewed the footage to find the two alligator clips touching. We also had inconsistencies in the turning of our potentiometers, both in number of turns and precisely turning the dial for each new data point. Another unforeseen issue with our data is the lack of specification for the frequency of data points taken. This didn't appear to cause issues with our data, but it is always wise to understand the rate at which data is being received by the computer. It was also assumed that the gauges were properly adhered and connected before our arrival in the lab. The Wheatstone Bridge's reliability, ease of use, and versatility make it an invaluable resource for the last half-century of engineering. Today, Wheatstone Bridge strain gauges can be found in countless applications for strain measurement. The F-35 Joint Strike Fighter, built by Lockheed Martin, used 20,000 data acquisition points for stress monitoring in its initial wind tunnel testing. The automotive industry uses strain gauges for crash testing and the residual stress and deformation caused by welding. We would like to thank Mr. Terry Lyles and Dr. Barnett for providing guidance during this exercise, as well as LeTourneau University for offering this opportunity.